Okay, so let's start to allow you to have more time in your presentation and also in the question and answer section. So good morning, everyone. Welcome to this April webinar about industrial symbiosis in mineral sector. Today we will have three speakers that I will present in a couple of minutes. But as always, just to remind you that this webinar is being recorded to be uploading to LIAISE COST Action YouTube channel. So I also kindly ask you to follow us in social media, not only in YouTube. We are also active in LinkedIn, Twitter, or X, and also Instagram. So please check our social media, follow us because the impact and the relevance of the action is a key factor for everyone. So just moving for the webinar of today, this April webinar about mineral sectors, we will have three presentations: long duration energy storage with circular economy, circular materials, sorry, synergetic co-processing of urban and industrial waste for metal recovery, and last but not least, industrial symbiosis business model for high purity quartz extraction from quartz mining waste. So, and after that, we will have the question and answer section. Regarding the speaker, we have three. The first is Stephen Frigerio, Maltese professional with over 10 years of international experience in sustainability, ESG, climate finance, and also innovation, not only in Europe, also through Asia Pacific area. He's specialized in business development, strategic partnership, and also stakeholder engagement. And he has been working with institutions such as the European or the World Bank. Now he is currently leading a startup acceleration initiative related to energy and climate, and he will explain a little bit that information during the presentation. Our second speaker is the professor Dr. Ersin Yazici, if I'm not pronounced wrong. He is a researcher and lecturer in the Division of Mineral and Coal Processing in the Department of Mining Engineering in one university of Turkey, concretely Karadeniz Technical University. His research focused mainly on the sustainable recycling and recovery of valuable metal from primary and secondary resources. Also, he is leading projects like European funded Eramin project, and also he is author and co-author of more than 140 scientific publications in peer-reviewed journal and international conferences. Last but not least, we have the Associated Professor of the Department of Surface Mining in Ukraine, Andriy Cherev. In 2002, he was graduated from the National Mining University within the degree in mining, and later on in 2008, he defended his PhD thesis. He conducted lecture and practical training mainly on the topic of technology of open cast mining of mineral deposit, mining processes, or even open cast mining. And apart from that, he worked on substantiating the factor of technological and economic approach to the assessment of production processes in mining sector. And also as professor, he has more than 50 published scientific papers. So welcome for all, for the three of you. Thank you so much for being here. And I don't not want to take more time on the floor. We will start with our first presentation, long duration energy storage with circular materials. So Stephen, the floor is yours. You could share your screen.
Thank you, everyone. I hope you can hear me well. I'll start to share my screen. I just sent you a request because I can't share my screen.
I think now you can.
Okay, now I see it. I hope you can see my screen.
Yes.
Super. Let me just try it. Super. So Excellent. Thank you very much. Thank you also for inviting me. I'm happy also to be part of this cost action as one of the working group members. And today, as mentioned, we'll be speaking a bit about a concept in long duration energy storage, but with the use of circular materials. Just a quick introduction about ourselves. We are a venture accelerator based in Malta. I've been working mostly in innovation acceleration for the past 5 years. Myself, I've been working in international development and cooperation in energy for more than 10 years and in innovation management support as well. So working a lot with different European, but also companies outside of Europe as well. Our aspect is mostly related to bringing innovations from the lab to the market, mostly related to the energy and storage sectors as well. We do a lot of different projects, also Horizon projects, but we also do ad hoc support to startups and companies that are working in these fields related to energy storage and also to renewable energy production. We have different sectors that we target related to either hydrogen, transport, hydropower as well. I'm working with different companies and institutes really in this field. So really scaling from low-level TRL, high-level TRL, and bringing some of these to the market. Given that we work in energy storage, we've been working recently with one of our partners in the UK, which I will be presenting to you today, focused on energy storage and circular materials. Before going into that, just a refresh of what energy storage technology we are talking about before introducing the company. Essentially, for all of you that may not work in the field of energy storage, there are different aspects and different technologies related to energy storage, including batteries, that you may know very well in recent times. But there are also other energy storage technologies such as hydrogen. The one that I wanted to talk to you about today is related to pumped hydro storage. Essentially, the concept is quite simple. Excess energy that is being produced by the grid needs to be stored in a pumped hydro storage situation. This renewable energy then gets used to pump water up on a hill. Usually, these are actually mountains in order to gain enough energy storage from these from the production, and is stored in a reservoir. Obviously, when there's an increase in demand, this is where the pump storage device is used. The production then is used to release the reservoir water from the hills from the upper reservoir down into the grid and generated through the turbine. And then this is the circular motion that keeps on repeating itself according to the demand and supply of the energy grid. Just a quick introduction then on the company that we're supporting here is called LIAISE. This company is essentially focused on a new novel technology. So as I was mentioning before, usually in order for pumped hydro storage to be efficient, the reservoir has to be stored in a mountain region in order to be efficient. In this case, excuse me, sorry. In this case, what the technology here is being, sorry, just one second, because I have a lot of background noise where I am. I hope you can hear me. Instead of actually storing the reservoir on a mountain in order to take advantage of the height, what LIAISE is developing is essentially doing the same concept of pumped hydro storage, but for smaller heights, what we call smaller heads. In order to do this, they are developing a technology which is essentially using a fluid, what they call a proprietary high-density fluid that is 2.5 times denser than water, of which you can actually get a similar power and energy, but with lower head, as I was mentioning before. So this is really a novel technology that is being used, and therefore this can get similar power and energy compared to having it on a mountain head. So obviously this improves the flexibility of how energy storage can be deployed and really expands the possibilities of how energy storage can be deployed. And I will go now into a bit more detail of the material itself. Before doing so, essentially right now, in terms of the technology, in terms of what it is able to achieve, the moment it's between 4 to 20 hours of long duration storage. Essentially, in terms of the project scale, we're talking about 10 megawatts to 100 megawatts range. And essentially, the core IP of this is really the mix of the fluids between the water, the proprietary material, and a circular material that is being used in conjunction to that. What is this material that is being used, and how is this used in terms of circularity? So essentially, the key component of this fluid that is used in the R19 fluids, as I said, it's a mix of water, it's a mix of other chemicals, but mostly it's related to barite. So barite is one of the key components of the fluid that is being used for this pump energy storage. And it is quite the key component of this fluid in order to create the fluid density that is used then for the pump hydro storage device. It is the weighting agent, as we call it, and this was mixed with water and the fluid, which is, as I said, that's the patent, the innovation, which is obviously the patented part of the fluid solution. So because of this, the barite then increases the fluid density by 2.5 times, and that allows the same amount of energy to be created, but at a lower head. Barite is being used also because of the fact that it is quite a common material, especially in mining waste. This was also one of the reasons why. And in order to create a very competitive solution, the company is looking into different options into using extracts of barite from existing mines. So there's a very increased use now of pumped hydro storage in mining sector, especially in disused mines, where potentially this key ingredient can be extracted, can be mined and used. When we talk about the volume needs, so in order to make this actually a critically efficient way of developing the fluids, essentially what we're looking at in terms of a commercial project is really about 250,000 tons of this material in order to create the fluids. So this is quite a large amount at the moment in terms of the pilot sites that we have developed, or that they have developed specifically. They are sourcing this material actually from abroad, outside of Europe, in order to create the proprietary pilot site that is currently at TRL level 6 to 7. But really the best way to make this more cost efficient and really competitive on the market is either to mine barite directly or use barite as the waste product. And this sourcing of the material is essentially one of the key components that we're looking into in order to scale this at a more competitive level. Talking just very briefly about the pilot site, the registration project. As I mentioned, this is based in the UK. It is at a site of a mining location in Devon. And it is done there to produce and to prove the capabilities. Right now, this pilot site is running at 500 kilowatts with a head of approximately 75 meters. The expansive turbine is, as I said, this is also the advantage of this is that at the moment, also during the pilot site, the existing turbines that are used in existing pump hydro storage sites are being used. So therefore, there is no need to develop new types of turbines to optimize the high density fluid. The research aspect and component of this is also related to how the fluid interacts with the turbines that are being exposed to the different types of fluid. Obviously, instead of water, this is a different type of fluid. So part of the research there is also going into how it interacts with the turbine and pump. As I said, this is the pilot site now at the moment is going at around 1 hour duration. Key component is the fact that we're using existing pump at the demonstration site. And really, in terms of improving the concept and increasing the capability of this design is really, first of all, what R&D we're looking into is the design of the pump to optimize the interaction with the fluids, but more specifically also with relation to how this is very relevant to this cost action, is really about the extraction of the raw materials and how this use is into integration of the design of the fluid. So really the circularity components for Re-Energize is really focused on using waste materials, especially from mining sites, using that, especially barite at the site, and really increasing the cost efficiency and effectiveness of the prototype. So just to conclude my presentation, really the types of research interests we're looking into and to cooperate with members even at within this cost action is really trying to understand the mineral supply chain. We really want to optimize this in terms of the efficiency. So looking at the sources, also looking at the quality of the barite, different processes, and all potentially even other alternatives to barite is something that we're also looking into, and to really end up with some finalized proof of concept and to see how this is more from the cost efficiency point of view in terms of the extraction and the refining of barite and other potential materials. We're also looking into using decommissioned mines as a research project. It could be coal, it could be other types of mining sites where we could extract barite. And then, as I said, the third potentially could be using mining waste as well. We were also looking into different research projects related to the extraction. So not necessarily the refinement, but the extraction of mineral waste. So we're very open to this kind of collaboration as well. This concludes my presentation. I hope this was very helpful and interesting. And if you have any questions or you would like to reach out, please do so. And we're happy to discuss more in detail. Thank you.
Thank you so much, Steven. I see two questions, so let's answer them before moving for the next speaker. The first one is how many tons of barite are needed right now? More than 200 tons, and not come from Europe as of now. What is the status with reusing barite waste? Where is the energy from the pan meter storage usage? Oh my God, so many questions. Let's go maybe one by one. How many tons of barite are needed right now?
So yeah, as I said, for a commercial project, it would be 250,000 tons in order to be commercially viable. In terms of yes, the very good question related to barite. So we've had multiple discussions with different mines in Europe. We found potential barite sources in the Balkans. In Balkan region, Poland to a certain extent as well. I think the key aspect here is not only the sourcing of the barite, because and essentially to make it more cost efficient, for the whole prototype, is that the device is also installed on site. We looked into. There's also, let's say, the more infrastructure risks and infrastructure challenges. So usually, for example, in coal mines, you have shafts, and in order to, let's say, to install a pump hydro storage device in a shaft is extremely costly as well. So we were also looking into coal mine heaps, for example, instead of actual coal mines, instead of installing it into the shaft, because there are a lot of technical challenges in reinstalling it into these lines, also for safety issues as well. Also, in terms of yes, so that was the first part of the question, I think, and the second part of that question, I think, as well. The status of reusing barite waste.
Yeah.
Well, at the moment, what I can say is that we're sourcing it from abroad. This is for the pilot site that we have in China. We're sourcing it from abroad, and ideally, we would like to have a sort of a clear understanding of the feasibility of having it extracted on site in different parts of Europe. So this is still work in progress. And then the energy for the pump hydro storage is used. Ideally, as I said, we are talking about these used mine sites, and sometimes these are there's also the possibility of other types of applications. So in existing mines that are operational. So some, for example, and this would come into the decarbonization of heavy industries such as mining. So it would be and also a possibility to install these in running mining sites, and so that energy would actually be used for existing operations. But from that point of view, I mean, of course, the energy then is used either to power small villages or towns, etc. In sort of the in the other scenario, which would be the disused locations. But where we took the mine as one example. The key aspect here is about the level of head, so 75 meters. We were also looking into caverns and other, let's say, locations where there is a 75-meter head. So I said coal heaps, they're not actually lines. So anything with that level of head is something also of interest. That was the first question. Where in the Balkans? Bosnia.
Okay.
Sorry, the first question related to the water influence to rheology, especially viscosity. I can't specifically answer that question because I'm not the technical expert on this. But as I said in my presentation, we're looking into how it is interacting now with the level of the turbines right now, and it's also something that is being done during the research. So this is all I can say with regards to that.
Okay.
And also that's also related to the last question as well. Unfortunately, I can't divulge this information at this stage. But again, if you have any questions, please reach out to me specifically related to the viscosity or even environmental impact. I'm happy to continue this discussion further.
Thank you so much, Steven. Let's move for the second speaker. Okay, we go for Ersin. The floor is yours. I think you
I guess you can see the
Yeah,
present.
we are seeing. If you could do full screen, please.
Yes.
Yeah, of course.
Thank you.
So the floor is yours. Thank you.
Thank you very much also for your kind invitation and coordinating this cost action. My presentation is on synergistic co-processing of urban and industrial waste for a metal recovery. So I'm a lecturer researcher in Karadeniz Technical University in Department of Mining Engineering in Division of Mineral and Coal Processing, and my expertise field is recovery of metals from different kind of resources. So I would like to first focus on the need for minerals and metals for the fight with the climate change and the green energy transition. So I mean there are quite different kind of metals and minerals are needed to produce the green energy technologies, including batteries, solar panels, etc. So we need tons of metals and minerals to decarbonize the global energy system. Let's a bit focus on, for example, copper. I mean, the figure shows that in the next 15 to 20 years, we need historical scale copper production. And renewable energy technologies are driving unprecedented demand. And considering our limited copper reserves, it is certain that we will face a big shortage on copper production as well as other metals. And to reduce the dependence to critical raw materials or strategic raw materials to other countries, European Union announced action plans to accelerate critical raw materials productions locally, reduce over dependence on China, and to strengthen the circular economic concept. But however, still the actual recycling capacity and recycling rates are quite lower than the targeted values. For instance, for rare earth elements, recycling in European Union is still under 1%. And the collection of end-of-life products in European Union is just 40, which is need to be increased. So the European Union also promotes recycling, valorization of urban mine to recover metals in these urban mines. I mean, including e-waste, which is one of the most important secondary resource, depending on its critical raw material and strategic raw material content. It contains quite high amount of copper, especially printed circuit boards. Its copper content may achieve up to 20%. I mean, it is quite high when compared to primary copper ores, which contain 0.5 to 5% copper. And in addition, of course, e-waste contain high amount of precious metals, I mean, including gold also. But these waste source also includes toxic elements, which is harmful to the environment if not properly managed. Another waste source that comes from the mining industry is pyritic tailings. These tailings is a byproduct of base metal sulfate flotation. Flotation is a method to used to separate minerals depending on its surface properties and with the modification of the surface properties of these minerals, making them hydrophilic or hydrophobic. Pyritic tailings has a quite high amount, and it should be collected in tailing stems. But there are some environmental risks. I mean, because it has the potential to generate acid mine drainage. With their contact with oxygen and water, it can release sulfuric acid, and coupled with the solution of some heavy metals, including iron or etc. But I mean, pyritic tailings in general, and the main component in the pyritic tailings is pyrite mineral. This can be used as an additive, in hydrometallurgical processes to facilitate the recovery of metals through different mechanisms. I mean, one of them is galvanic mechanism. This is used, previously it's a patented process called Galvanox. These processes use pyrite to facilitate the solution of copper from chalcopyrite or sphalerite. And the pyrite also can be used as a reducing agent source for leaching of pyrolusite, and as well as a lithium-ion battery black mass, which is another an important urban mine. And in our case, I mean, I will elaborate more in the following slides. It can be also used to increase the dissolution of copper from electronic waste. So I would like to shortly underline that the amount of pyritic tailings is high recently, and it's also getting much higher because mining operations is, going to be processed at and under deeper levels, and also the ore grades are declining. So that means we are producing more tailings, and also considering the increasing production demand for green transition, digital technologies, etc. So let's focus on the galvanic leaching mechanism. These findings is from our recently published study. We use the pyritic tailings we collected from a company located in Turkey. And we use these pyritic tailings together with the electronic waste in the leaching stage. So as you can see in the table, copper is less noble than the pyrite. So that means with the contact of a metallic copper in the e-waste, with the pyritic tailings, the electrons flow from copper to the pyrite, which means that the copper acts as a anode that dissolves, and the pyrite mineral acts as a cathode that does not dissolve in the solution, but catalyzes the copper dissolution reaction. So our studies revealed that with no addition of pyrite, we got only 14% copper dissolution, which is quite low. But with the addition of pyritic tailings to the leaching reactor, our copper extraction increased to 79%. And using natural pyrite instead of pyritic tailings, these recovery also increased to by up to 1980%. So using pyritic tailings in general in the leaching of e-waste brings quite advantages. As you can see in the table, the reaction it improves facilitates the copper dissolution. So it catalyzes the reaction, so it accelerates the reaction speed, and it also reduces the usage of expensive oxidants in the leaching. So this brings an important advantage is in also cost also. So we in this process we can valorize pyritic tailings, an important tailings material produced by mining industry, and on the other side e-waste, which is an important secondary resource as an urban mine. So in general, we can say that we have mainly three criteria in the process development for hydrometallurgical processes. So bringing the pyritic tailings into the leaching in a hydrometallurgical flow sheet, that brings significant advantages. It accelerates the copper dissolution, so it reduces the use of expensive oxidants. So this reduces the costs also, and using a tailings material also lowers the environmental footprint of the process. And for conclusions, there is a need for increasing critical raw material recovery from urban mines, improving the recycling rates from these mines with lowering environmental impact, and also reducing capex and opex is of practical importance, and also it is promoted by European Union also. So in our case, as I explained, a low value in industrial waste, this is pyrotic tailings, can transform leaching performance of a low-grade urban waste stream, which is, e-waste, which bring significant benefits. And also, this is a quite nice example of industrial symbiosis also. So my presentation is over. Thank you for the attention, and I will be happy to answer questions if any.
Thank you so much, Ersin, for your presentation, interesting presentation. For the moment, I don't see any question in the audience, so let's move first to Andre, and later on in the question and answer section, we will see if there's something. So, Andre, the floor is yours. You could share your screen and start also your presentation. You are mute.
Can you hear the
Yes.
can you see the presentation? Of course.
Yes,
So,
please do just
okay. Okay.
full mode and we'll be.
Just a moment. Yeah.
Okay, perfect. Thank you so much.
Yeah, good. Yeah. Hello, dear colleagues. My name is Andrei Cherep. I'm presenting our research conducted together with my colleague, Dr. Daria Pilova. The topic Industrial Symbiosis model for high purity quartz extraction from quartz mining waste. This study addressed the intersection of critical materials, sustainable resource management, and circular economy innovation, focusing particularly on the case of Ukraine. Modern challenges of sustainable development require rethinking traditional approaches to the use of natural resources, in particular in mining industry. In the context of growing demand for high-tech materials, high-purity quartz is of particular importance as it's a critically important raw materials for producing solar panels, semiconductors, optical glass, and other products with high technical requirements. At the same time, the global deposits of high-purity quartz are extremely limited, which stimulated interest in finding alternative sources of its production, in particular from mining waste. Quartz sand waste, which is formed during the extraction of titanium ilmenite ores, is a potential source of high-purity quartz in Ukraine. The integration of industrial symbiosis approaches based on cross-sectoral cooperation and waste reuse open up new opportunities for increasing resource efficiency, reducing environmental burden, and creating added value within the framework of circular economy. Ukraine has significant accumulated quartz sand waste, which can serve as the basis for the development of industrial symbiosis business models to meet the global demand for high purity quartz. Therefore, an analysis of potential for using waste from Ukrainian mining and processing enterprises.
Sorry, Andre, sorry for interrupt you. Are you changing the slides?
Yeah.
Because we are not seeing. Okay, and also
Okay.
I don't know why we have.
It's introduction.
Okay, but let me comment that there is like a kind of sentence about Zoom behind that doesn't allow us to see the full screen. Also because I don't know if you took something, but at the same time that you are speaking, you have like the subtitle, and that's hide the presentation. So if
Okay.
okay, now better.
Yeah.
Thank
Oh,
you.
sorry. Step 1 analysis of the potential for using waste from Ukrainian mining and processing enterprises. Sorry. Just a moment. Oh my God. Oh, I don't understand how it switch off rapidly. So let's begin with the context. Silicon dioxide or silicium-2 is a vital component in modern technologies. While abundant of the Earth's crust, only a tiny fraction is suitable for application requiring ultra high purity, such as semiconductors, solar photovoltaics, and optics. This slide presents the segmentation of the global silicium-2 market. It illustrates how high-purity quartz plays a fundamental role in high-tech industries. Yet production of high-purity quartz is limited, expensive, and environmentally taxing, typically centered around a few locations globally, like spruce pine in United States. Next slide. High purity quartz is defined by its extremely purity, often requiring impurity levels below 50 parts per million. High purity quartz applications are divided into three major segments. The first one is semiconductor industry, which use it for crucibles and wafers. The second part, the solar PV sector, where ultra-pure quartz is required for producing polysilicon and the solar cells. And the third one, optics and glass industry, which values quartz for its clarity and thermal stability. Global production is not keeping pace with demand, and current processing technologies are highly energy intensive, especially for growing single crystal silicon from polysilicon melt. This drives the need for alternative, more sustainable source of high purity quartz. The market for semiconductor silicon continues to grow as modern information technologies, computer electronics, telecommunications, etc., are based on its use and will continue to be based on it. The production technology of high purity quartz includes several key components: raw material selection, processing technologies, processing equipment, and quality control systems. These elements form a comprehensive system consisting of independent yet interrelated and interdependent processes. HPQ is characterized by an extremely low levels of impurities, less than 20 ppm according to the Unimin IOTA CG standards, and is an essential material in many advanced optoelectronic industry. Various processing technologies can be used to produce high purity quartz, namely crushing or sorting, flotation, leaching, roasting, separation, and other technologies. Often a combination of different technologies is used to produce high purity quartz. The ongoing search for HPQ deposits and source is driven by a shortage of suitable clean quartz deposits that meet modern industry standards. Therefore, choosing a specific beneficiation technology for HPQ depends on the deposit's geological structure or type, environmental impact of processing method, and its cost effectiveness within the operational context of mining enterprises. Next slide. Semiconductor technology involved the global trade in devices continues to rise, both in volume and strategic importance. Now, this slide shows a sharp increase in export of semiconductor devices worldwide and within the European Union. What this means is simple. The demand for HPQ is not a niche phenomenon. It is central to global digital and energy transitions. Complementing exports, the import dynamics illustrate the dependency patterns. The European Union, for example, imports a significant portion of its semiconductors despite ambitions to boost domestic production under initiatives like the European Chips Act. As countries look to secure supply chain, the availability for HPQ, particularly from non-traditional and sustainable sources, will become a key differentiator. This slide visualizes global trade in semiconductors over nearly 3 decades. Asia Pacific dominates with Europe and Americas trailing. This underscores the strategic pressure to diversify source of critical materials like HPQ and build resilient supply chains that are both local and circular. Let's now move to Ukraine. Ukraine possesses substantial mineral wealth, including large deposits of quartz and quartzite in regions such as Zhytomyr, Dnipro region, and Kirovohrad is the central part of Ukraine. The average quartzite deposits alone contains over 150 million tons of high silicium O2 raw material, comparable to the highest global standards. However, these resources are underutilized. Most production is geared toward low-grade applications like construction or metallurgy. Most production is geared towards low-grade. Our study investigates whether quartz mining waste, particularly from titanium ilmenite extraction, can be upgraded into high-purity quartz. Ukraine titanium ilmenite mining generates millions of tons of quartz and waste. It's situated in the Dnipro and Zhytomyr region, two big mining and processing enterprises. Titanium, traditionally considered unviable, these tailings may actually contain relatively clean quartz with low titanium and sodium impurity levels. Our mineralogical assessment confirmed that with proper beneficiation, such as magnetic separation and acid leaching, this waste could meet HPQ standards. This represents a powerful waste to resource opportunity under the principles of industrial symbiosis. Here we see Ukraine's position in the global quartz market. Despite abundant resource, Ukraine mostly export low purity quartz in raw or semi-processed form. Industrial Symbiosis offer a model to transform this low-value waste into high-value product by fostering collaboration between mining companies, processors, and high-tech manufacturers, Ukraine can reposition itself within critical materials supply chain. Let's now address the enabling environment. Ukraine has made progress in adopting circular economy principles, but industrial symbiosis remained underdeveloped. Key policies include the law on waste management, aligning with EU directives on prevention, reuse, and recycling. It's a second one, national waste management strategy until 2030. The next one is a low carbon development strategy until 2050, and recent amendments promoting eco-industrial parks. In conclusion, our study shows that Ukraine has the geological resources, industrial base, and the strategic potential to become a key player in high purity quartz market, especially through the valorization of quartz mining waste. The first one, the high purity quartz, is critical to semiconductor, solar PV, and optics. Global demands is growing rapidly, but production is limited to a few countries. Ukraine has the really big resource base, but these materials are often treated and waste. And processing technologies exist, such as magnetic separation, roasting, acid leaching, and chlorination, many of which can be adapted to local conditions. And policy reform is essential to enable industrial symbiosis, industrial parks, tax incentives, cross-sector collaboration, and regulatory clarity. Thank you very much for your attention, and I look forward to your question.
Thank you so much, Andrei. Thank you for your presentation. We have a question in the chat. Is for Ersin. Ersin, are you there? Yeah, okay.
Yes.
What are the following steps now that you have seen that period can be used in this way? What are your challenges to scale if this is what do you want to do?
Right. Thank you. This is a very nice question. I mean, in developing hydrometallurgical processes, regeneration of the reagents, acids or oxidants, is practical importance. In terms of also cost, especially. So this is a labs case study, of course. But after the leaching stage, which we used, e-waste and pyretic tailings together, we need to separate and recover these pyretic tailings and to be reused in the leaching stage again. So this could be a problem, but theoretically, pyretic tailings is quite a fine material because it's already crushed in the ground and subjected to flotation. So maybe, some simple sieving can be used to separate pyretic tailings, to separate from the leach residue of the e-waste. And one problem could be also, it is a readily available tailings in worldwide, but of course, the logistics aspect should be also considered before building a continuous operation, and there may be some arrangements in the policy side maybe can be needed also, and one thing could be the control of iron in the solution. E-waste can contain also some iron, and depending on the leach conditions, these pyretic minerals, pyretic tailings, can release some small amount of iron also maybe. But this depends on the leach conditions. But the iron level should be controlled also in the leaching stage. Actually, iron also is beneficial in the leaching stage in ferric form as it acts as an oxidant, but it should be also, I mean, also controlled. I mean, this could be also I mean, important in a continuous operation. Where these are some concerns about the scaling up of our proposed galvanic leaching. Thank you. You are muted, Almudena.
Oh my God, sorry. Thank you so much, Ersin, for your answer.
Welcome.
And I was asking if there is more question from the audience, but if not, I think we are going to close because it's already 12. So thank you again, Steven, Ersin, and Andrei, for your presentation, for the information that you provide, and also for the support of the action with this webinar. As always, the recording will be available in the next week, and also I will share with all of you the presentation. So once again, thank you so much, and have a nice weekend. We are in contact, and
Thank
see
you,
you
Almudena.
in main webinar. Bye.
Thank you
Thanks,
very
bye.
much. Bye.